The topic of chapter 3 is rigid body motion. In the previous lecture, we have known that a minimum 6 number is required to describe the rigid body motion, including the position and orientation in the three-dimensional physical space. In this chapter, we will develop the systematic way to describe the rigid body position and orientation. Actually, it depends on the attachment of a reference frame to the body. Okay, as you can see in the previous lectures, the 6-parameter representation is required to describe the rigid body motion. So it will be defined as an exponential coordinate in this chapter. And pre-vector will be defined as a geometric quantity with the length and direction. Actually, pre-vector is not rooted anywhere. So this vector with the same length and the same direction, maybe both are same pre-vector. And the coordinate-free concept will be explained in the later. Okay, it does not have any coordinate frame. Coordinate-free concept is more general to describe the rigid body motion. And then if you attach some reference frame, then the numerical coordinate value appear. And then we will derive the twist. Maybe the next week I will talk about the concept of length. Okay, let's assume that we have a coordinate-free point, just P. In here, if we attach the frame A here, using the XA and YA coordinate axis, and then by projecting the numerical value to the XA axis and projection of YA axis, then we can get the coordinate value. So the coordinate free point P can be described as a numerical value using the frame A. On the other hand, if we attach another coordinate frame B, XB and YB, then we can get another description of a point P position. So for the generality, we will introduce two frames. Space frame denoted by the S, body frame denoted by the B. Space frame will be defined as an absolute frame, such as the corner of the room or at the ground, substantial ground of point. The body frame is defined in the moving body, such as the mass center of the moving body. Like this, the body frame will be fixed to the body, but if the body moves, the body frame is move as well. Okay, the all reference frame are right-handed. Okay, if the index finger is aligned to the x-axis, middle finger is aligned to the y-axis, then if we make the curl motion from like this, then the thumb direction will be used as a g-axis. This is called as a right-handed rule. Through the textbook, we will use right-handed coordinate. Okay, section 3.1, rigid body motion in planar case, in the plane. Okay, the space frame is attached to the ground, and the body frame is attached to the rigid body. So, in here, we can get the origin of the frame B is pointed by the P vector. It will be obtained by the 2 and 1. So we have this one. In here, XB axis can be described using the XS and YS. Maybe using the projection to the x-axis and the y-axis. Then we can get the cosine and the sine. So we can describe the xb using the xs and ys. On the other hand, yb can be described by using the xs and ys using the cosine and sine convention. It's not difficult, it's easy. Anyway, the body frame position P can be expressed in terms of the coordinate axis of the S. In here, 2 is the coordinate value, 1 is the y-axis coordinate value, and the coordinate is defined 1.0, 0.1. Then we can get position vector of the P. On the other hand, we can get the orientation. The xb axis is obtained by the projecting this unit vector into the xs and the ys axis. I'm sorry, this is the typo. This is the hat ys. This is also a typo. Okay, I'm sorry. Anyway, the cosine theta will be the projection value of the xb into the x-axis. So the cosine 60 degree will be the 1/2, and the sine 60 degree is the square root 3/2. So we can get the unit vector of the xb in terms of xs. Using the similar procedure, we can get the yb hat. So we can get it. Okay, like this. If we agree to express everything in terms of the space frame S, the point P can be represented as just column vector P. On the other hand, two vectors xb and yb, the unit vector of the frame B, can also be written as a column vectors and packaged into the following 2x2 rotation matrix. It means this vector is the xb, this vector is the yb. Actually, the rotation matrix has the 4 elements, 1, 2, 3, 4, like this. But we have the 3 constraints, such as the first unit vector is the normal, the second unit vector is also normal. We have 2 constraints, and orthogonal, the inner product of the first one and the second one will be the 0 because both are orthogonal each other. So we have 3 constraints. So one remaining degree of freedom is parameterized by the angle of rotation. So from now on, we will use the pair rotation matrix and pointing to the origin of a point base frame. This pair will provide the description of the orientation and the position of the B frame relative to S, or in terms of S. Okay, this is the space frame fixed to the ground. This is the body frame. And then we have another C frame. Okay, in here's XS, XC, and YC. As mentioned before, this B frame can be expressed by the rotation P and pointing P vector. Okay, so the pair will describe the base frame B. In here, the origin of frame B will be described 2x2 because we have the 2 unit and the 2 unit. And the orientation matrix can be described. Okay, the XB can be lead from the S frame. Maybe the XB will be equal to the YS axis. It means 0.1. So we have the first column. And XB can be led in terms of S, so minus XS direction. So -1, 0 will denote the YB axis. Thus, okay, let's remove here one more. Okay, the C frame can be described by B frame. Okay, rotation angle will be the psi, and the pointing vector is the q. In here's the q vector is described using the b frame, -1 and the -1. So we have the -1 and -1. The rotation matrix q can be described by using the psi, angle of the rotation psi. So we have this equation. Actually, the xc can be led using the xb frame. It will be equal to the yb axis, so xc can be described by the 0.1. So we have this one. On the other hand, yc can be led by using the b frame, maybe the -1, 0. So we have the second column of the q matrix. Okay, like this, the P and P is obtained in terms of the S. Q and Q is obtained in terms of the P. Okay, if you know the Q and Q and P and P, then we can compute the computation of the C relative to S, not B. Okay, the rotation matrix Q, if we want to base frame into the space frame, then the rotation Q should be multiplied in front side. So we can get this kind of equation. Actually, the P matrix acts like operator to convert Q to the S frame. This Q vector is described in terms of the P. This is also changed into the S by multiplying the rotation matrix P. So the Q is converted to the S frame using the P matrix, and then vector sum is achieved by adding a P. Then we can get the R vectors. Okay, in here we can know that the rotation matrix acts like operator to convert to reference frame. Okay, rigid body displacement, rigid body motion is described as two sequential transformation. In the previous page, we know that the first rotation is achieved, and then the displace of the position. So the rotation matrix vector pair R and R of the C. So this is described. R and R will be moved to the C prime. Will be denoted by the R prime and R prime. Okay, in here, R prime can be obtained by rotating the rotation matrix R by multiplying the P matrix as operator. It will be described in terms of the S. So the transformation rotate base frame at C according to the P. Okay. On the other hand, the transformation will translate it by the P in S. Okay, in here's this R vector. By multiplying the P matrix, we will get this one. This is equal to PR in terms of the S. By adding a P, by vector sum, we can get this vector that is equal to this one. So rotation matrix vector pair can be used for three purposes. The first one is to represent the configuration of a rigid body. This is the transitional law of the rotation matrix. On the other hand, to change the reference frame in which a vector or frame is represented, it means though this operator can make the frame change. On the other hand, it can displace a vector or frame, as you can see here. Okay, one more. Let's introduce the screw motion here. Actually, this rigid body is rotated and translated, then we can get it. Okay, if you consider this kind of motion, we can get some point. This point is chosen, and then if we apply some rotational angle beta here, then we can make the same movement. Is it right? Let's assume that the rotation velocity SO1. Then the fixed space frame will move like this according to the rotational movement. Maybe this value will be this is 2 units, so x directional velocity will be 2. There is no 0 velocity in the direction of the y. So the screw axis is defined like this. All the times 1 radian per sec is applied to the rotational axis. Then the space frame base will move to the 2 and the 0 like this. Okay, actually it expressed omega and Vx and Vy. Okay, as mentioned before, it will be always all the time as a 1, and then this is the velocity, linear velocity of base or fixed frame, space frame. Okay. Like this, by using the rotational velocity and the linear velocity of the space frame, we can get the screw axis notation. This is the screw axis. Okay, by applying the rotation angle like this, rotation angle can be multiplied to the screw axis. Then we can define the exponential coordinate. And then let's apply the theta dot, actual theta dot, not 0, not 1. Actual angular velocity is applied to the s-axis, screw axis. Then we can get the combined linear and angular velocity. This is called as twist. So first concept is the screw axis, second one exponential constraint, third one is the twist. Those concepts will be used through the textbook, so you should understand in depth. Okay, the more important one is the screw axis. Rotational center should be obtained, and then the space frame like this. You should know the displacement to here. Then let's assume that so 1 radian per sec movement of rotation. Then this point will make the linear motion, maybe the Vx and the Vy. By combining this one and this vector will consist of screw axis. Okay, let's summarize in the next page. Okay, the screw movement. Screw motion. Okay, the rigid body motion expressed as a rotation followed by translation can be obtained by simply rotating the rigid body about the fixed point by an angle beta. Maybe for the generality, it can be replaced as a theta. This is the planar example of the square motion. Okay. Okay, for the notation of a square axis, rotating about S with the unit angular velocity, each very important concept. Unit angular velocity is applied to the square axis, will produce the point at the origin of S frame moves at a 2 units per second initially in the x direction in the previous page. So we have the 2.0 as a linear velocity of a space fixed frame. Actually, this is a virtual velocity, not actual. We can package these two notations in the three vectors, the omega and the Vx and Vy. Okay, as according to the assumption of angular velocity, it will be the all the time 1. And the linear velocity of the origin of a space frame. Then we can define the square axis. Okay. Following the square axis, for the angle, let's assume that theta as a pi over 2, 90 degree. In here, by multiplying the s theta will produce the final displacement of the rigid body motion in the planar case. So the square axis times scalar value theta will be called as exponential coordinate for the planar rigid body displacement. Okay, square axis multiplying the theta dot angular velocity will be defined as a twist like this. So we take the square axis as in here all the time we assumed that omega s as a 1, but if you apply the actual velocity of the actual angular velocity, then we can get the combined linear and angular velocity of the rigid body motion. It is called as twist. Okay. Actually, the net displacement obtained by rotating about the square axis by the angle theta is equivalent to the displacement obtained by rotating about s at the speed theta dot as a theta per unit time. Okay, let's assume that 3 radian per sec. It can be interpreted 3 radian per 1 second. Is it right? So if you assume that all movement is finite in 1 second, at that time theta dot is equal to all the time theta. Like this, the twist can be interpreted as a exponential coordinate as a special case. Okay, the preview of the remainder of this chapter, we will extend the planar movement into the 3-dimensional case. So according to the right-hand rule, the g coordinate will appear satisfying the x times y as a z. If we use the x times y as a minus z, at that time we are using the left-hand rule. But we will keep the right-hand rule, so by making a curling motion from the x to the y using the right hand, some direction will be the g. Okay, like this we can define the space frame, and let's attach the body frame like this to the center of mass of the rigid body. To describe the rigid body motion, the p and rotation as a 3 as a 9 elements will be required to describe the rigid body motion. So the point P can be expressed like this, and the rotation matrix will be described by leading the x-axis and the y-axis and the g-axis in terms of the S frame. as a 9 element. Like this, we can get the pair of the R and P to describe position and orientation of rigid body in the three-dimensional physical space. In case like this, we will extend the position and orientation. You should remember that the 12 parameter is used to describe this one and this one, but in there, only 6 elements are independent.